All right, and we're just going to end by talking about shells and how to find gravity inside of a planet. So for this one, we'll use a very powerful theorem from Newton, which says that the gravitational force experienced inside of a planet is simply just equal to the mass that's below you, as long as the planet's uniform. And it might seem initially strange that that means that everything above you can be ignored. So, for example, if we think about this mass piece right here, uh, this side of the planet, or the shell, is definitely much closer to M, so it's going to experience a lot of force from that piece of the planet downwards. But it turns out that exactly in all cases, that's balanced by the fact that the farther away pieces of the mass uh, give more contribution. So one of them is closer, but the other has more area, and those effects exactly cancel each other because it turns out they're both quadratic in nature, right? Doubling the radius quarters the force, but it also doubles the area because it's pi r squared. So that's the shell theorem. So for us, all that means is that if you're finding the gravitational force or field, you're just looking what is below you at that instant. And if you have a uh, spherical planet, you can think of building it up as a bunch of shells. And we'll go through an example explaining how to do this. But if your planet has uniform density, that means that the mass beneath you is just going to be the mass of the shell, which is just the density times the volume, which you can think of as some sort of a volume fraction times the total mass. But first, for a simpler example, we're just going to deal with the planet is composed of several concentric shells of uniform density. We want to find the gravitational force on a person of mass m at all these different spots. So here's the center of the planet, and we have a bunch of shells. So this is not a solid planet. There's just a bunch of hollow shells. So we are just going to use the fact that Newton's law of gravitation can actually be written as F is equal to G times M times the mass enclosed by the circle at your radius divided by r squared. So the big M in gmm over r squared is the mass enclosed by your circle. So first, if r is less than or equal to a, that's this first shell right here, well, if I draw myself a little circle here, and I look at the mass that's enclosed, it's zero. There's nothing enclosed. And that seems odd, but it is true that if you're in the center or just anywhere inside a shell, you experience no net gravitational force. So F is, of course, equal to G times M times enclosed mass divided by r squared. But the enclosed mass is zero. But then as we start to move out, so it's actually zero everywhere inside this inner region. But as soon as we move out into the second region, we do in fact get a gravitational force now. So if I just pick some location R that's in the second region, well, now I'm enclosing the first shell. So I'm going to get F equals G times M times mass of the first shell divided by r squared. And that's a constant. So it's constant everywhere in the middle region. So my force has increased a little bit. And now similarly, if I move out to this in-between region, once again, I've enclosed another shell. So my force is going to enclose both the mass of the inner and middle shell. And that's also constant everywhere in the middle region. And then lastly, if I go all the way out, well, I'm just enclosing everything now. So I just enclose all the mass. So F is equal to G times all of the mass. Which should make sense, because when you're outside the planet, it is just going to be gm over r squared. So that's just going to decrease then. So if you actually think about graphing this, the answer definitely depends on what the actual masses of the shells are, and how they compare. But we're likely going to get some graph that looks like something like this. So it's going to be 0, and then we'll mark off some regions. So we'll mark off our first shell, our second shell, our third shell here. So we're going to get something that, depending on what the masses look like, it could look something like this. And now for a more typical calculation of finding g inside of a planet. Instead of finding force, which is object dependent, we like to find the value of g, which is called the gravitational field, which is just the gm over r squared, but with the little m factored out. So since the gravitational force is equal to g times m enclosed divided by r squared, the gravitational field, which can be just written as the force with the little m divided out, is just g times enclosed mass divided by r squared. So to do this, all we have to do is figure out how much mass is below us as a function of the radius r from the center. So outside the planet, it's pretty straightforward because it's just going to be the total mass and gm over r squared, just as per usual. But inside, we have to figure out exactly how much of our total planet mass is inside versus outside at that moment. So we do that just by assuming constant density. So for inside, we have that g is equal to gm enclosed divided by r squared, which is equal to g times the mass inside is equal to density times volume divided by r squared. But then also, since density is a constant, we can just use the m over v for the whole planet for density. So g is equal to big G times density, which is the mass of the planet divided by the volume of the planet, because total m over total v gets us density, times the volume inside the shell, and then we divide by r squared. So now we start plugging in. So we get g times m times r, or divided by r squared, times the volume fraction. So first, let's figure out what volume is enclosed. Well, it's going to be a sphere of radius little r. So that's going to be 4/3 pi times little r cubed. And then for our total, it's just a sphere of radius big R. We can see that the 4/3 pi's cancel, as well as 2 of the r's. So we get gm over big R cubed, which is a constant, times r. So gravitational field is actually linear inside the planet. So it increases linearly up until you get to the outside. So again, all we did is we said that the enclosed volume is a sphere of radius little r, so volume's 4/3 pi r cubed with the little r. And then we said that the total volume is just a sphere of radius 4/3 big R cubed. And then outside the planet, well, it's quite simple. Because outside the planet, well, you're never going to gain more mass outside the planet, so it's just gm divided by r squared. And notice that is our typical value of g that we saw before. It just falls off like the inverse square law. So g actually increases as you move from inside the planet to the edge, because you're enclosing more and more mass. But then after, you stop enclosing more mass, so it just falls off like the inverse square law. Now let's graph the field as a function of r. So we see that there's a really critical change point here. So we said that g is equal to gm over r cubed times r if r is less than big R. And we said that little g is equal to gm over little r squared if r is greater than or equal to r. So what that physically looks like, if this is our point r, so again, inside the planet, our field is increasing at a constant rate because you're enclosing mass at a constant rate. And then you've reached your maximum g field value here. So this is proportional to r. And then as soon as you reach the planet and start leaving the planet, well, it falls off like 1 over r squared. So we get this shape. And lastly, let g sub 0 be the gravitational field strength at the surface of the planet. Where will an object experience a field strength of 1/2 g naught? Give both locations. So what we're saying is, if g naught is the value of g at the surface, which we said before is just equal to gm divided by r squared, where big R is the radius of the planet, where can we get a field strength of 1/2 g? So just based on the graph, we can see that there will be 2 locations. So if this is half the maximum, we can see it does intersect twice. And we want to find what those values are. So first, inside is very straightforward. I won't even work it out mathematically, because we can just kind of see what the answer is, because it increases linearly. So g is linear inside. So at 1/2 of a radius, we get g is equal to g naught divided by 2. Because it's just increasing linearly. So if you want 1/2 of the surface gravity, you just got to go halfway to the surface. But then outside, here's where we have to actually set up an equation. So outside, we want g is equal to 1/2 of g naught. So we know that g is defined outside the planet to be gm divided by r squared, and g at the surface is gm divided by r the planet squared. Cancel out big G and the m. And we get that r squared, little r squared, is going to be equal to 2 times big R squared, or R, is just going to be equal to square root of 2 times R of the planet. And I should use. And there's our answer. Or you could just see that, well, since it's inverse square, you got to have a square root of 2 in the denominator to make it twice as large, because the squaring will remove the square root. So notice very different behaviors. Inside it is just linear, but outside we have to account for that inverse square law behavior.